Imagine two particles, as tiny as you can imagine, linked together in a mysterious dance. They are connected. When one spins one way, the other spins the opposite way, instantly. This is the baffling phenomenon we call quantum entanglement. It's as if these particles are communicating faster than the speed of light, no matter how far apart they are. This is not science fiction. This is the reality revealed by quantum mechanics, the physics of the very small. It's a world where the rules of our everyday experience seem to crumble. A world where particles can be in multiple states at once, called superposition, and where their fates are intertwined in this ghostly dance of entanglement. But how can this be? How can two particles influence each other instantaneously across vast distances? These are the questions that have puzzled physicists for decades, ever since the early days of quantum theory. Even Albert Einstein, one of the founders of quantum theory, was troubled by entanglement. He called it spooky action at a distance. He believed that there must be some hidden variables, some yet-to-be-discovered properties of the particles that could explain their seemingly magical connection. Along with his colleagues Podolsky and Rosen, Einstein proposed a thought experiment in 1935, now known as the EPR paradox. They argued that if quantum mechanics was complete, then entanglement would imply faster-than-light communication, which contradicted his own theory of special relativity. Einstein believed that there must be a simpler, more intuitive explanation, one that preserved the principle of locality, the idea that objects can only be influenced by their immediate surroundings. For decades, the debate over entanglement remained a philosophical one, but in 1964, physicist John Bell devised a brilliant way to test these ideas experimentally. His theorem, known as Bell's theorem, provided a way to distinguish between the predictions of quantum mechanics and those of a local realistic theory, like the one Einstein envisioned. Bell showed that if Einstein was right, there would be limits to the correlations that could be observed between entangled particles. But if quantum mechanics was correct, these correlations could go beyond those limits, violating what became known as Bell's inequalities. Bell's theorem transformed the debate about entanglement from a philosophical quagmire into an experimental quest. It gave physicists a clear target to aim for, a way to settle the argument once and for all. Section 4. Through the Looking Glass, Experimental Confirmation. In the 1970s and 1980s, a series of groundbreaking experiments, starting with those by John Clauser and Alain Aspect, began to test Bell's inequalities. The results were astounding. These experiments and many that followed consistently showed that the correlations between entangled particles violated Bell's inequalities, exceeding the limits imposed by local realism. These experiments provided compelling evidence in favor of quantum mechanics and entanglement. It seemed that Einstein's intuition for once had failed. The universe was indeed stranger than he could have imagined. These early experiments, while groundbreaking, were not without their loopholes. But in recent years, physicists have conducted ever more sophisticated experiments, closing these loopholes one by one. Section 5. A new era of quantum technologies. The implications of entanglement extend far beyond the realm of theoretical physics. Entanglement is not just a strange curiosity of the quantum world, it's a powerful resource that is driving the development of revolutionary new technologies. One of the most exciting applications is in the field of quantum computing. Entanglement is the key ingredient that gives quantum computers their immense computational power. By harnessing the superposition and entanglement of quantum bits or qubits, these computers have the potential to solve problems that are intractable for even the most powerful classical computers, with applications in medicine, material science, and artificial intelligence. Another promising area is quantum communication. Entanglement can be used to create ultra-secure communication channels, potentially unhackable. Imagine a world where sensitive information could be transmitted with absolute security, immune to eavesdropping. The strange and counterintuitive phenomenon of entanglement is opening up a new frontier in science and technology. As we delve deeper into the quantum realm, we are only beginning to uncover the true potential of this remarkable phenomenon. The future is entangled,